In this lecture, we are going to study about what is hysteresis curve and how to classify magnetic materials as either soft and hard magnetic materials. This is Unit 5, Lecture 6. First, we shall see what is this domain theory of ferromagnetism. According to Weiss, the specimen of ferromagnetic materials have number of regions or domains which are spontaneously magnetized. In each domain, spontaneous magnetization is due to parallel alignment of magnetic dipoles. The direction of spontaneous magnetization varies from domain to domain. The resultant magnetization may hence be zero or nearly zero. Now, when an external field is applied, there are two possible ways for the alignment of domains, either by motion of domain walls or by rotation of domains. Now, in this diagram, which is a domain, each region over here is called as the domain and they have a dipole moment. And these dotted lines over here are the domain walls. Now, by motion of domain walls, the volume of domains that are favorably oriented with respect to the magnetizing field at the cost of those that are unfavorably oriented. So here initially you would see the diagram, the total value is equal to 0, no external field is applied. When you apply an external field in this particular direction, the volume of one region becomes more, the volume of other regions will become less because this domain's dipole moment is in the direction of the external field. Next, by rotation of domains, when the applied magnetic field is strong, rotation of the direction of magnetization occurs in the direction of the field. So they will rotate and get oriented in the direction of the field. So essentially, when you apply external magnetic field, the domains will move, or the dipole moments will move in such a way that all of them will get oriented in the direction of the external magnetic field. Now, hysteresis. The hysteresis of ferromagnetic materials refers to the lag of magnetization behind the magnetizing field. Both are not in phase. In the absence of a magnetic field, the domains in the material are randomly oriented, as you would say, and the resultant magnetic moment is zero. When an external magnetic field is applied, the domains get oriented in the direction of the external field. So you can say the domains are all oriented in the direction of the external field over here. Now we shall see what is hysteresis curve based upon domain theory. A, we have H, external magnetic field, and B, the amount of flux density developed in the material. Okay. Now, as the external magnetic field H is increased, the magnetization of the material proceeds along path 1. This is the path 1 from O to A. Point A indicates saturation of magnetization, that even if you increase H, okay, B will not increase, it remains constant. All the domains are oriented in the direction of the external magnetic field. So this is no saturation of magnetization. When the external magnetic field is reduced back to 0, the magnetization curve takes path 2, that is from A to B. It does not come back from A to 0, but it takes another path, path 2 from A to B. Now, the original path 1 is not traced because of irreversible processes occurring in the course of demagnetization. Defects such as impurity atoms, dislocations, and non-magnetic inclusions present in the materials affect the motion of domain walls. Domains retain their original orientation even when H is equal to 0, leading to remnant induction Br. So though we are still further decreasing over here, you can see though H has become equal to 0, B is not equal to 0. There is some amount of magnetization that is present, OB. That is known as remnant induction or retentivity. Now, elimination of the remnant magnetization, that is reaching the point C, requires the applied field H in opposite direction. So you are applying H in the opposite direction, then you reach the point C. That point is known as coercivity. The amount of energy spent to reduce the magnetization to 0 is called coercivity. Now, point D indicates the saturation in the opposite direction. If you still further go in the negative direction, we reach another saturation point, but this saturation point is in the opposite direction. So here you can see at point A, the domains are in one direction. Here the domains are in opposite direction, but both are in the direction of the applied field. Here the applied field is in one direction. Here the applied field is in the reverse direction. So the entire thing makes a curve, closed loop. What is hysteresis loss? It is the loss of energy in taking a ferromagnetic body through a complete cycle of magnetization, and this loss is represented by the area enclosed in the hysteresis loop. So this is the hysteresis loop having an area, and the area enclosed by the hysteresis loop gives you the loss. Now based upon that, we can classify materials either as soft or hard magnetic material. Okay. So once again, your graph between H and B, here the area is less, here the area is more. Area is less is soft material, area is more is a hard material. The process of magnetization of a ferro or ferrimagnetic material consists of moving domain walls so that favorably oriented domains grow. If the domain walls are easy to move and coercive field is low and the material is easy to magnetize, such a material is called soft magnetic material. If it is difficult to move the domain walls, the coercive field is large, then the material is magnetically hard. These are called hard magnetic materials. So we are going to discuss about soft magnetic materials and hard magnetic materials and see the difference between them. What are soft magnetic materials? Soft magnetic materials have low hysteresis loss due to small hysteresis loop area, whereas hard magnetic materials have large hysteresis loss due to large hysteresis loop area. In soft material, the domain wall moment is relatively easier. Even for small changes in the magnetizing field, the magnetization changes by large amount. In hard materials, the domain wall moment is difficult because of the presence of impurities and crystal imperfections, and it is irreversible in nature. In soft materials, coercivity and rotativity are small. Hence, these materials can be easily magnetized and demagnetized. Whereas, hard materials, the coercivity and rotativity are large. Hence, these materials cannot be easily magnetized and demagnetized. Next, soft materials are free from irregularities. The magnetostatic energy is small, whereas in hard materials, because of the presence of impurities and crystal imperfections, the mechanical strain is more. Hence, magnetostatic energy is large. In soft materials have large values of susceptibility and permeability, whereas hard materials have small values of susceptibility and permeability. Soft, these are used to make electronic magnets, whereas hard, these are used to make permanent magnets. So these are soft are usually electromagnets, okay, and these are permanent magnets, hard magnets. Applications of soft magnetic materials mainly used in electromagnetic machinery and transformer cores, whereas hard magnetic materials for production of permanent magnets used in magnetic detectors, microphone flux meters, and loudspeakers. So in this, we have seen what is domain theory of ferromagnetism. Then we have seen how what is hysteresis and what is hysteresis losses, and how to classify materials as soft materials as well as hard materials.